Okay, so this is a recording of additional material that I didn't cover in lectures, but is nevertheless important for understanding the material of the course. And this is about, it's a second part of concurrency control. And what I'm going to talk about is the snapshot isolation. So in the assignment that you had, well, last Wednesday, you had one isolation mode that was called snapshot isolation that didn't reflect anything that you had seen from the logging. And this is a snapshot, it's a isolation mode that is now optional in SQL Server and probably fairly commonly used. It has been used in Oracle for a long time, in PostgreSQL for a long time as well. And so this is one of the most common isolation modes, and this is why I want to talk about it in more detail. Now, this is implemented using something called multi-version concurrency control, which is based on timestamps. And so I'm actually going to talk first about a simpler method based on timestamps that is important to understand, and then extend that into the multi-version concurrency control. Now, this is covered in chapter 17.6, but I would actually recommend to look also at the Wikipedia entries that I've put there, because they have some fairly good details. Okay, so let's go into this timestamp, timestamp-based concurrency control, and then the multi-version concurrency control. Now, the main idea of timestamp concurrency control is to give each transaction sort of a timestamp when it begins, and this could be a number that is simply incrementing, or it actually could be the time when it starts. It's important that they have unique timestamps, because you want to be able to use this to detect conflicts. And the main idea about conflicts between timestamps is basically based on the same conflicts that we talked about when we were talking about locking. Remember the write-read conflict. When somebody wrote something, somebody else wants to read it, and the first one hasn't committed. Then you have a conflict. If you have a write-write conflict, somebody writes something, somebody else writes it, and this is a conflict, and so on. And so the rule of this timestamp concurrency control is that if you have two transactions, Ti and Tj, and Ti is doing some action that conflicts with the action of transaction J, and transaction I started before transaction J. So first transaction I starts, then transaction J starts. Then it's important actually that the operation of transaction I must happen before the operation of transaction J. So meaning that if you have transaction 1 here, transaction 2 here, and then doing something, and then this operation is, let's say, writing an object A, and then transaction, I was going to indicate that transaction 2 started after, so we'll do this like this. So, and then transaction 2 wants to write something. It's okay if that happens after, but not if it were to happen before. Now, using this rule, you might have to compare every transaction to every other transaction, and also every action of that transaction to every action of any other transactions. So this would be complicated, but for easy detection, you can actually give each object a read timestamp and a write timestamp. So read timestamp of a particular object and the write timestamp of a particular object. And what these mean is basically the time of the timestamp of the transaction that last read it or last wrote it. So when a transaction 1 reads an object A, the read timestamp of the object gets assigned the value, the timestamp of transaction 1. if transaction 1 writes object A, then the write timestamp would be given the value, the timestamp of the transaction 1. So these are maintained basically as objects are being read and written. And all right, so let me back up. So basically, just to correct slightly, what this should be is basically the maximum value. So the highest timestamp of everybody that read it, the highest or the last write timestamp. So look at this. Let's say a transaction wants to read an object O. So there are two cases that might be there. One is that the timestamp of the transaction is less than that of the last write. This means that somebody wrote the object after that transaction started. And we just say, this is a violation, there is a conflict, and we abort the transaction. When it gets restarted, it should have a new larger timestamp, or if it's started by the user, then it will get a new larger timestamp, because otherwise it would fail again. Because you would have the same situation that the timestamp of the transaction would still be smaller than the right timestamp of the object. Now, if the transaction started after the last write of the object, then the transaction is allowed to read the object. And we set the read timestamp to the maximum of the old read timestamp and the new and the timestamp of the transaction. This means that if the transaction is the most recent transaction to read it, this timestamp wins. If somebody or newer transaction has already read it, that timestamp wins. And there's an additional thing that this has to be written to disk for recovery, and this actually, and the restarts that we had here are some overheads of this. So as with locking, there are some overheads. You cannot get concurrency control without any overheads. But it's a fairly simple test. So each object has two values, the read timestamp and the write timestamp, and based on that, we can make a decision whether to abort or to allow the write, or to allow the read in this case. Now, it's a little bit more complicated with the write, because there are basically three cases. So the first case is that you have a transaction that wants to write an object, but actually somebody already read it later. Somebody that started after you has already read the object. And in that case, there's a conflict. So if you were allowed to write it, then that would invalidate the read that the other transaction already did, and we cannot have this, and so we abort you. We abort the transaction that wants to write the object. There is another interesting case, and this is actually quite brilliant, is that what if nobody has read the value, but somebody has actually written the value? So nobody has read the value that was after after your transaction started, but somebody actually wrote it. This would violate the timestamp order of your transaction with respect to the writer, that the transaction that actually wrote the object. But the solution to this is actually not to abort and restart, it's to do nothing. And this is really important. So this is based on the Thomas Wright rule, which says that you can safely ignore these. And what's actually going on is that you have sequences like the one shown here, where you have a transaction reading something, you have another transaction writing an object, and then possibly committing, and then you have this transaction writing and committing. And remember, in locking, this would not be allowed, because you have a read lock here, you cannot write, and so this one would happen before. So you would effectively, you can think of with locking, you would move these up and you move these down. Now, by using this rule of doing nothing, then you basically, when this situation happens, so let's remove the thing that happened with the locking. When this thing happens, you simply ignore this write. And that's exactly as the same as pretending that it happened before this one, and this one happened after this write. So by this Thomas Wright rule and by ignoring this write, we are simply doing the same thing that locking would do, but with less overhead, because we only had to check timestamps. Now, if your timestamp is greater than the read timestamp and the write timestamp, then that means that you have the last version and you're allowed to write it. And this is no problem. So that's the last case here. So the first one is obvious. Somebody read it already, you cannot write it. This one, somebody wrote it, but actually, because of this rule, nobody has read the value after you started. And in that case, you just do nothing, because your write would effectively be overwritten anyway, and so you don't need to do anything. And then if nobody has, if you're the last thing to touch this, then you're allowed to proceed. So these are the two things that describe what you do when you have readers and what you do when you have writers. Now, it turns out that the timestamp, as we described it, may give you unrecoverable schedules. So remember, what's unrecoverable? It means that if we were to crash, we couldn't recover. And so this is an example of that here. Somebody writes an object, somebody else reads that value, makes a decision, writes a B, and then commits, but we haven't actually, this guy might abort. And so there is a read-write conflict here that we didn't resolve. So this, of course, can be modified by to allow only these recoverable schedules. And the trick is to buffer all your writes until you commit. And then you have to block readers. So basically saying so if we raise this, you can say that when this guy here wants to read the value that has been updated, where the timestamp is greater than the write timestamp, then we just block until we get a commit, and then we proceed. And so this is kind of similar to the writers holding exclusive locks, but it's still not quite the two-phase locking. But it will give you recoverability, which is very important in databases. So that was the timestamp thing. And that the reason for explaining this is basically to understand what is a transaction timestamp, what's a read timestamp, what's a write timestamp, so that it's easier to understand the multiversion concurrency control. And because that one is actually also based on timestamps. Differently from the other one that you had, we are now not just working with a single version as before, but we're making basically copies of the version of the objects and keeping them in a version pool. So we have the main segment, which has the current version, and then we have a version pool which has essentially a linked list of older versions, and we can traverse this linked list until we find the version that was in action, basically, that was appropriate for our timestamp. So the version that was in effect when we started. And this means that the readers are always allowed to proceed, but for recoverability, as before, we may block readers until we commit writers. So if you are reading something that has been updated by, within your correct timestamp, by a transaction that hasn't committed, then you will have to wait. So readers may be blocked, but they don't have to get any locks, and they can essentially that way always proceed, and they will not be aborted. Now, if we go back to the timestamp, what was the reason to abort a reader? Well, it was if somebody had overwritten what you wanted to read. But in multiversion, then we don't overwrite. So we still have the copy in effect. And that's why readers can always proceed, or they will never be aborted. Now, for each version of this object, you have a writer's timestamp as the write timestamp, or the transaction. The timestamp of the writing transaction is the write timestamp, And the timestamp of the transaction that most recently read that particular version is the read timestamp. The chain backwards, as I said, we can discard versions that are too old to be of interest. And if you think about what's too old to be of interest, then it's basically copies written by transactions that have committed, or you can say if you have a timestamp range for a copy and there are no transactions with that timestamp in effect, then it can be discarded. Now, many systems will actually, for space reasons, they will discard old versions, even though there might be transactions in effect. And so in that case, you may get some errors like snapshot too old or something like this. And that's basically means if you have very, very long reading transactions, you may run into trouble because of too many copies or not enough copies being maintained. Now, you can classify transactions as readers or writers, and the writer may write some object and the reader never will, and you have to declare in the beginning whether it's the reader. And the reason for this is because for readers, you do something slightly simpler. So when you're a reader, if you need to read an object, what you do is you find the newest version with the right timestamp smaller than your timestamp. So you just go back in the chain. Remember, you have some lists and you find, okay, this version is the newest version that was in effect when I started. And that's about it. You basically now you assume, by assuming that there's a version of every object, then reader will never be restarted. And why should there not be a version of every object? If you lose a version of the object, then you're in trouble. Now, but again, the reader might block until the writer of this commits, but this is the same. This is just to ensure recoverability. So readers are simple. You just traverse the linked list of copies until you find the right one to read, and that's it. And then you can continue. Writers are more complicated. So if they are reading, then they follow the reader protocol. But when they are writing, they need to find the latest version such that the right timestamp is smaller than the timestamp of the transaction. Now, this is interesting because this is a version here. This is the last or the newest version that is smaller than the timestamp of the transaction. But as it happens, there is a newer version that some other transaction has written. And so you might ask, how can this be? How can I actually be allowed to update something that has already been updated? Sounds crazy. But the trick is same as with the Thomas Wright rule that we had before, is that it's, is that this is basically somebody just will overwrite your value. Because this write timestamp is greater than your timestamp, this means it's a transaction that started after you. And so if that transaction starts after you, it will simply overwrite your value, and this is fine. You will have a write here that will exist for some time, and then it will get lost, and that's okay. And this is basically the same Thomas Wright rule that we had before. Okay, so if, on the other hand, and this might be the more complicated case, okay, so if the read timestamp is smaller than your timestamp, that means you found a version that was in effect, which is the blue version, and you just discovered that nobody read it here. If somebody read it, they read it here before you're about to write it. That means that you won't invalidate any reads, and so it's safe to update it. If this is not the case, if there is actually a read here, then you would invalidate some read and you reject the write and you in fact abort the transaction. But if the read timestamp is smaller than your timestamp, then what this transaction does is make a local copy of the value and give that read timestamp equal to your timestamp, and then the write is actually buffered until you commit, so that the other transactions will actually see the timestamp values, but they can't read your version. And so this is the same. You basically are blocking the readers from reading your version. And so with this protocol, with the multi-version concurrency control, it's interesting that you may actually not, as you're writing, you may not be always making a newer version than others. You may be making a version that is actually older than something that's been updated since. But again, because you're working with the timestamps and everybody else is working with the same timestamp protocol, this is fine. Everybody will read the version that is appropriate for their timestamp, for their beginning, and there will be no conflict. Writes are buffered so that readers have to block until the appropriate transactions have committed, and so it's recoverable. And so it's actually a very clever algorithm that is based on having this chain and just working with this chain. And so if you might actually have new versions being 1.5 being inserted into the pool because it's being updated at the at an intermediate time. So now it's not perfect, however, and so there's a well-known thing called the write skew anomaly that can happen with multi-version concurrency control, which basically violates serializability. And so if you consider a following sequence, you have two values that are not the same, two database objects that in the beginning are not the same. And then you have two transactions, T1 and T2, that intend to make them the same. So what could happen is that T1 reads the two values, sees that they're not the same. Then concurrently, T2 is reading the two values and seeing that they're not the same. T1 decides to update, basically to assign to V1 the value of V2. T2, on the other hand, decides to update to value V2 the value of V1. So this could be something like two triggers deciding to balance some value, two values, and their updates are being made to them by different transactions. So what you actually have is basically at the end, what you've done is a swap of the two values, which is not what you intended because you wanted to keep them the same. And if they were not the same in the beginning, they won't be the same at the end. So this schedule is not serializable because here the T1 would get read locks on value 1 and get a read lock on value 2. And here transaction 2 would get a read lock on value 1 and a read lock on value 2. And then you would basically have a deadlock. This guy would try to upgrade the locks, and this guy would try to upgrade the locks, and you have a deadlock. Or alternatively, if you start by giving exclusive locks here, then this guy will have to wait. And so you won't be swapping, you will just serialize the thing. So basically, this schedule is not serializable. It wouldn't occur with strict two-phase locking, but the multi-value concurrency control, it allows it. Now, if you tell this to a native Oracle person, they will just say, of course, this is the way it should be. And not knowing the theory of serializability, they would think that this is perfectly normal. However, one of the reasons why they think so is because this mode is actually called serializable in many cases, and which is not correct. And so this is the confusing part. What is correct is basically that this multi-version concurrency control implements snapshot isolation very well, and so this is the mode isolation mode name in SQL Server is actually the appropriate one, snapshot isolation. So just to summarize, there are ways of doing concurrency control that I've mentioned briefly before, which are called optimistic, basically assuming that there are no conflicts and then dealing, discovering and validating the writes that happen. I won't talk about this because they are not used in practice, but I did talk about timestamp concurrency control, which is a simpler version of the multi-version one. And just to introduce the concepts of the timestamps in the simpler fashion. And then I talked about the multi-version concurrency control, which ensures that read-only transactions are never restarted. They can always read the suitable older versions. They might be, if you might have to block to wait until commit. And there is some overhead, of course, of a version maintenance because you keep around many versions. And so in a situation where you have high update loads with some long reader transactions, there actually may be cases of snapshot too old errors, which are problematic. And the trick there is actually to break the reading transactions up into smaller ones and just ignore the fact that this might lead to some non-serializable behaviors. And then we talked about in this case also that you may have this write skew anomaly. It's something that happens rarely, but it's important to know of it and realize that this basically violates serializability. In most cases, it's an acceptable trade-off for the performance gains that you get in the multi-version concurrency control, and this is why people simply accept it. All right, so that was it, and then enjoy working this out. Thank you.